Welcome to the second lecture on analysis of vibrations. So in this lecture, I will concentrate on trying to describe the vibrations of a 2 degrees of freedom system, or a system that can be sufficiently accurately modeled as 2 degrees of freedom. Basically, what I mean is, if you have let's say a 2-story building, or the fan and blower system that we were talking about at the beginning of the first lecture. The foundation can be thought of as a mass. Its connection to the ground can be thought of as a spring, and the structural damping that it has can be thought of as a damper. And then the motor and the blower can be thought of as a mass, and that's its connection to its supports to the foundation can be thought of as a spring, and its structural damping as a damper. So that system, or a 2-story building, for example, can be approximately modeled as a 2-mass system coupled to each other through springs and dampers. Springs capturing the stiffness of the couplings, and the dampers capturing the structural damping of the coupling. So if you can do that, or as a first approximation, we may try to understand the system in this way. And so what is the advantage of doing this? So this allows us to think of the system in a very simple way, and consider each of these masses separately, consider the forces acting on it separately, and apply Newton's equation. So if you take the reference point from the equilibrium points of the system, so you just leave it there, and there is no motion, it settles to a certain equilibrium point. And if you mark the equilibrium points of the two masses, the center of mass of the two masses, the location of that at the equilibrium point, and then when this moves about that equilibrium point, if you take those displacements as x1 for this mass and x2 for this mass, and write down Newton's equations, you get this set of coupled differential equations. So in assignment number 2, I have assignment number 3 actually, I have asked you to derive these equations by considering the free body diagrams of these masses separately, and considering the forces acting on the masses separately. So the advantage of this is that what we see is that, so now you have two second order differential equations, they are coupled to each other, they are coupled with each other. And since it's a mathematical object, we can find solutions. And the hope is that the solutions of this differential equation sufficiently capture the physical behavior of the system that we want to model. And so let's try to see how we can do that. So the first thing that we will observe is that this system of coupled differential equations can be written down in a matrix form, as a matrix differential equation of this form, where M is this matrix, 2 by 2 matrix, C is this 2 by 2 matrix, and K is this 2 by 2 matrix, and X is x1, x2, these two displacements put in a column matrix. So this is x1 dot, this is x dot, and that is x double dot. So what we see is, if you have a system that can be, as a first approximation, considered to be two masses coupled to each other through springs and dampers, apply Newton's equations to arrive at a coupled set of second order differential equations, and we see that those coupled set of differential equations can be written down as a matrix second order differential equation. Now, in the previous lecture, we had a similar situation where now instead of matrices, we had scalars for the displacement, and the mass was a scalar, damping was a scalar, and the stiffness was a scalar. However, now we are still in the same situation if you really think about it, but the only difference is now what we have is a matrix differential equation. So we can try to apply what we have done in the previous lecture for the single degree of freedom basic vibrations for this coupled system by looking at the matrix differential equation. So with zero initial conditions, if you take the Laplace transform of both sides, which is what we would have done in trying to solve the first order, the 1 degree of freedom vibration system in the previous lectures. So if you take the Laplace transform of both sides, you get this expression over here, where x of s is the Laplace transform of x, and f of s is the Laplace transform of the matrix f of t. So remember that now these are matrices, these are column matrices, because these are column matrices. So when you mean by taking the Laplace transform, you take the Laplace transform of each of the elements. And so if you have this, now this is a matrix polynomial. If you take the inverse of the matrix polynomial, x of s can be written down of delta of s inverse, this matrix inverse of that, times f of s. And so using Kramer's rule, we will find that that will be something like this, where this matrix is that. And so if you apply Kramer's rule, we will get something like this, where G1s is this and G2s is that, and F1s is the Laplace transform of the forcing function applied to the first mass, as we saw it in the previous figure. So these things I have asked you guys to derive in your assignment number 3 and assignment number 4. And so please go through the details, and also you may refer to the lecture note for the derivation of these results. So the bottom line is, we have a matrix differential equation, just like before for the first order, 1 degree of freedom, not first order, 1 degree of freedom system. You apply Laplace transforms to both sides. Now you can't just divide by the polynomial. Instead, you have to take the inverse of it, which is, since this is a matrix differential matrix polynomial. And so when you do that, you get this expression over here. You apply Kramer's rule, and then you see that x of s, x1 of s times x2 of s is equal to this and that, a column matrix, where G1s is given by this and G2s is given by that. And this is the determinant of this matrix polynomial, as we would get typically when we apply the Kramer's rule. So now, in order to find x of t, so what is x of s? X of s is the Laplace transform of x1 of t and x2 of t, the column matrix. So if you take the inverse Laplace transform of that, you will get x of t. And so we take the inverse Laplace transform of this whole thing, and then we will get x1t and x2t. And so in the special case where the forcing function is a sinusoidal function, if you take the inverse Laplace transform, you will get just like in the previous case, because now notice that it is taking the inverse Laplace, is taking the inverse Laplace of that, taking the inverse Laplace of this. So this is now again a scalar rational function. This is a scalar rational function. And when f of s is the Laplace transform of a cosine function, we saw that in the previous lectures, that, and in assignment number 2, that the inverse Laplace of this is something like this, and inverse Laplace of that is something like this, where the amplitude magnifications are simply the magnitude of G1s replaced by I omega and G2s replaced by I omega, and the phase is simply the phase of the complex number G1s replaced by S replaced by I omega and S replaced by I omega in this case. So let's take a closer look at what this. So let's take a closer look at this one, the displacement of the first mass. So what we notice is the first mass also moves with the same frequency as the forcing frequency, with two differences: amplitude is magnified, phase is shifted. Second mass is also moving at the same frequency as the forcing frequency, but with the amplitude magnified and the phase shifted, where the amplitude magnifications are given by this and the phase shifts are given by that, with these transfer functions found to be from the Kramer's rule, as we discussed in the previous section. And so let's look at this amplitude magnification. So what is this? This, if you try to compute this, and if the amplitude magnification of that using this, you see that you get this denominator, which is the determinant of the matrix equation, matrix polynomial. And if you replace s with I omega, you get a polynomial in I omega. Now, if in the case where the damping is 0, this will be 0, and that will be 0, and that will be 0. And what we would notice is that we have a fourth order polynomial, in omega. Or in other words, we will have a second order polynomial in omega squared if the damping is 0. If you take a closer look at this, you will see that when you replace s with I omega and set the damping to 0, you will get a polynomial of omega squared, second order polynomial of omega squared. So what that means is you will get, and you can show that there are 2 real roots for omega squared. So you will have 4 values of omega plus and minus each. And therefore, when the damping is 0, the denominator will be 0 for 2 values of omega. And that's what you see over here. And therefore, the amplitude of magnification will be infinite at those two values of omega. And actually, there are 2 minus values. And so we will only consider the plus value. And so what does that mean? What that means is the amplitude magnification becomes infinite at 2 frequencies. In the 1 degree of freedom case, we had only 1 frequency, and we call that the resonance frequency. And in this case also, we find that they are also called the resonance frequencies. And when the damping is small, the amplitude magnification will not be infinite, but be some finite value. And the resonance frequencies will be close to the undamped resonance frequencies, but not exactly equal to this. So that is basically what we see over here. And so like in the 1 degree of freedom case, you have resonance, but only difference is now you have 2 resonance frequencies. Why? Because this polynomial is a 4th order polynomial in omega. Thank you.